Now we need to discuss about the matching functions. In the last class, we were discussing about Boolean search, then symbol searching strategy like that. And in this matching functions, what do you mean by this? Here, all the sophisticated search engines are implemented by means of a matching function. This is a function that will find the similarity between a query and a document. So this is a function similar to an association measure that we already discussed, but differing in that a matching function measures the association between a query and a document or a cluster profile. But the association measure is applied to the objects of same kind. The association measure is a measure which is used to find the similarity among different documents. But here, matching functions are finding the similarity among a query and a document, like that. Mathematically, these two functions have the same properties, they only differ in their interpretations. So here, the matching functions, we need to discuss it in detail. Some example of some matching functions. We need to discuss about some examples of matching functions. Here the simplest matching function is the symbol matching search strategy that we already discussed in the last class. Then another example is Dice's constant, Dice's coefficient. This coefficient is used for calculating the similarity between a query and a document. If M is a matching function, here you can see that M and D is a set of keywords representing the documents and Q the set of representing the query. Then you can find this matching function as 2 into D intersection Q divided by D plus Q. Here this means we are taking the number of words, find number of words which are common for both D and Q, and we will be multiplying that with 2 divided by number of words in the document and the number of words in the query, and we will be finding the summation in the denominator. This coefficient is known as Dice's coefficient. This can also be used as a matching function in order to find the match between a query and a document. Another example of a matching function is cosine correlation. That is the cosine similarity among different queries and different documents. They are used by the project called SMART and assumes that document and query are represented as numerical vectors in T-space. That is, Q can be represented as Q1, Q2, Q3 up to Qt, and D can be represented as D1, D2, D3 up to dt, where Qi and Di are the numerical weights associated with the keyword I. The numerical weights means what? The number of times that word is repeating in the query or the document. Then the cosine correlation is, now simply you can say that R equal to sigma t equal to 1 to t qi di divided by root of sigma I equal to 1 to t qi square into sigma I equal to 1 to t di square. This is our cosine correlation. Cosine correlation is used where and when these documents or queries can be represented as vectors. This vector contains some weights, numerical weights. This numerical weights may be what? The number of times that particular keyword is repeating in the query or the document. Or in a vector space notation, we can rearrange, or you can rewrite this equation as R equal to Qd divided by Q into D. Here you can see the cosine similarity is what? The dot product of two vectors divided by the product of their magnitudes. Here that is cosine theta, where theta is the angle between the vectors Q and D. So these are some examples of matching functions that we can use to find the similarity between a query and a document. Now we need to discuss about what a serial search is. From the word itself, we can understand that we are serially searching something. We are serially searching what? We are serially searching the documents for a particular query. So in serial searching, what we do is we will search all the documents for the query sequentially, and we will be calculating the similarity score or the matching function. That is what is happening inside the serial search. But all the serial searches are acknowledged to be slow. These searchings are slow because it is sequential. But they are frequently used as part of larger systems. They also provide a convenient demonstration of the use of matching functions. We will be finding the similarity or the dissimilarity by using these matching functions that we discussed. Suppose there are n documents di in the system, then the serial search proceeds by calculating n values m d qi, that is a set of documents to be retrieved, is determined. From the values of these matching functions, we will be selecting the number of documents to be retrieved to the user. So once these matching values are found, we can select the retrieved documents by using two different ways. The first one is the matching function is given a suitable threshold. Then we will be retrieving the documents above that threshold only, and we will be discarding all the documents below that particular threshold. That is, if T is the threshold, then the retrieved set B is a set of di where m, q, I should be greater than T. The matching score should be greater than a particular threshold, then only that particular document will get retrieved. Then the second method it is very similar to the first method. The documents are ranked in increasing order of matching function value. Then we will be selecting a rank position R as a cutoff value. And all the documents below that particular rank are retrieved, so that B equal to di, where Ri should be greater than the cutoff ranking. Here Ri is the rank position assigned to di. So we will be retrieving all the documents which has a rank less than the cutoff rank. Okay. Here the assumption is that in each case the relevant documents are contained in the retrieved list. That is the assumption. The main difficulty with this kind of search strategy is the specification of the threshold or cutoff. The specification of the threshold or cutoff means arbitrarily we will be selecting this threshold and cutoff. It will change according to the situation and circumstances. So there is no definite theory behind this. How can you select the threshold or the cutoff ranking? It will always be arbitrary, since there is no way of telling in advance what value of each query will produce the best retrieval. So we will be experimentally calculating the values of threshold and cutoff. Now we need to discuss about the cluster representatives. We all know that the serial search is very slow process. It will take a lot of time. So people think like this, how can we reduce the searching time? And they come up with a solution like that. We will be clustering the documents and selecting a representative from that particular cluster. The clustering means we will be collecting the documents and we will be grouping those documents according to some general criteria or some similarity among these documents. And we will be selecting a representative from that. Then we will be comparing the input query with those documents only. Means we will be comparing the query with the cluster representatives only. Then if there is a match found, we will retrieve all the documents inside that cluster. That is the idea behind this cluster representative. So a cluster representative attempts to summarize and characterize the cluster of documents. The cluster representative should be such that incoming query will be diagnosed into the cluster containing the documents relevant to the query. Then this cluster representative discriminates the relevant from the non-relevant documents when matched against any query. Unfortunately, here also there is no theory behind to select the right kind of cluster representatives. So one can only proceed experimentally. But there are some reasonable number of reasonable ways of characterizing the clusters. It then remains a matter of experimental test to decide which of these is the most effective. One of the methods is finding the maximally linked document. Here you can see two clusters A and B. You can see some nodes, some dots. That dots are actually our documents. Then you can find some links or lines between different nodes. That line means the relation. If two documents are related to each other, then we'll be putting a line between those dots. So here we assume that clusters are derived from a cluster method based on dissimilarity measure. Then we can represent each cluster at some level of dissimilarity by a map, by a graph. Here you can find, we already discussed this thing, these dots are documents and lines are the relationship among different documents. If there is a similarity, we will be putting a line between these two nodes. In maximally linked documents, what we do is, we will be trying to achieve those nodes which has got maximum links. Maximum links means it will summarize or characterize that entire cluster. Here you can see A, there is an arrow. That arrow representing node is the maximally linked node or maximally linked documents. In the second cluster, in the cluster B, you could see two nodes which has got maximum number of links. That is the node, the arrow showing first node, then the second node which is showed by that arrow, which has got two links. So maybe we won't be getting a definite node, or we will be getting some more than one nodes which has got maximum links. Then we will be selecting those two nodes. So here you can see A and B are two clusters. The nodes represent documents are the line between any two nodes indicates that their corresponding documents are less dissimilar than some specified level of dissimilarity. Node means documents, that line means the relationship or the similarity between two documents. One way of representing a cluster is to select a typical member from the cluster. A simple way of doing is to find the document which is linked to the maximum number of other documents in the cluster. So a suitable name for this kind of cluster representative is the maximally linked document. In the clusters A and B illustrated, there are pointers to the candidates. Here you can see that pointers or arrows to the candidates. Those nodes are our candidates. In some cases, representatives may not be unique. We already discussed that. In the cluster B, we will be having two representatives. For example, in cluster B, we have two candidates. To deal with this, one either makes an arbitrary choice. We can arbitrarily select one node, or maintains a list of cluster representatives for that cluster. Hope it is clear. We will be maintaining a list of cluster representatives. Otherwise, we can arbitrarily select one representative. Hope it is clear.